Hello and welcome to the YouTube video channel of CRC768. My name is Debayan Roy and I will take you through the talk on inconsistency management through automated synthesis of control software for mechatronic systems. To start with, let us take an example of a mechatronic system such as modern cars. Now, most of the innovation in a modern car is through software running on CPUs connected over bus systems. Moreover, large part of this software is actually composed of control functions. For example, cruise control, brake control, engine control, etc. Now, for control functions, the control software synthesis can be partitioned into two phases, the controller design phase and the software implementation phase. In the controller design phase, a control engineer basically designs the controller based on the system model and the requirements using closed loop simulation and analysis. In the implementation phase, the software parameters are synthesized based on the designed controller and the constraints imposed by the implementation platform. Finally, the software is tested, and if some higher level control objectives are not satisfied, then the two phases are reiterated. Now, there is an inconsistency in this current design paradigm. The inconsistency lies in the fact that the control engineer makes certain assumptions of the platform which may not be satisfied by the implementation. In such a scenario, the control engineer says that his or her design is perfect and the problem lies with the implementation. While on the other hand, the embedded systems engineer says that the assumptions made by the control engineers are wrong. So this is a deadlock. We may also say that there is a semantic gap between the model and the implementation. Now the question is, how can we close this gap? And the answer lies in controller architecture co-synthesis, where both the control engineer as well as the platform engineer decides on some common model for co-synthesis of controller and implementation parameters. It must be noted at this point that the inconsistency in the current design paradigm can be resolved through automated co-synthesis of controller parameters and the implementation parameters simultaneously from joint controller and architecture specifications. This co-synthesis is possible by studying the interplay between the controller parameters and the implementation parameters. Subsequently, we can derive constraints from this interplay so that we can systematically take this into consideration in the co-synthesis approach. Based on this analysis, we have come up with a two-stage co-synthesis approach which can synthesize software for multiple control applications running on a shared platform. So in the first stage of this approach, we study the platform characteristics and determines the choices of sampling periods for the controller design. Subsequently, for each control application, we design prospective optimal controllers at each possible sampling periods. Now, based on the results from stage 1, we actually formulate a multi-objective optimization problem considering the constraints from the platform as well as the requirements from the system. Now, the formulated optimization problem is very complex in nature, and therefore we have to employ a customized hybrid optimization technique to solve this problem. And this hybrid optimization technique that we have come up with consists of two nested layers, as can be seen in this slide. Furthermore, we have also observed that the existing tools for the design and implementation of these systems is actually inconsistent with the co-optimization approach that we are proposing. Correspondingly, we have developed an integrated COTS tool support for the design and implementation of this system, which binds our co-optimization approach into the existing tools. Moreover, it automates the complete process. As can be seen in this slide, we also tweak the current design flow a bit according to our proposed tool chain. So this is what we have done so far. Now I will talk about what we want to do in the future. So in the future, we want to consider a complex mechatronic system such as hot rolling mill for steel, which takes as input a steel plate and the output product is a steel coil. Now, design of such systems require coordination and collaboration among various disciplines. For example, the product department specifies the properties of the material based on which the mechanical department actually designs the structure of the rolling mill, the hydraulic systems, so that the required force can be generated. Subsequently, the electrical engineers selects the motor which can provide the required tensile stress corresponding to the required rolling force. And finally, the software is for automation is synthesized, which in itself is a collaborative work of several engineers, for example, control engineer, system engineer, software engineer, etc. Now it is clear that the design of such a mechatronic system will involve heterogeneous models from various interacting disciplines. The problem with such collaborative engineering is that each participating discipline undergoes its own innovation cycles. And it is always desirable to incorporate new innovations onto the existing system. However, such an integration can result in change of the initial models. On top of that, the business requirements can also change. Nevertheless, both change in models as well as change in business requirements can actually lead to inconsistencies. And it is very important to detect and manage such inconsistency with a low-cost solution. So in this context, the first work that we want to do is interdisciplinary inconsistency management. We have established from our previous works that the control software synthesis strongly depends on models from other interacting domains. Now, if one such model change, then it may result in change in requirements, plant model, or reference of the control systems. And any such change can actually lead to an inconsistency. Now the question is, how can we resolve such inconsistency? So the most important thing is to first detect the inconsistency, which we can do by simulating the existing control software with the current plant model as well as the current reference, and see if the current requirements are met or not. In case there is an inconsistency, we can actually resolve such inconsistency using automated resynthesis. So with the help of interdisciplinary inconsistency management, we can actually resolve inconsistencies in the process which is directly impacted by a change. However, in complex mechatronic systems, many processes are actually interdependent on each other, which means like change in one process can actually lead to an inconsistency in another process. So to resolve or to manage such inconsistency, we need to come up with an inter-process inconsistency management framework. Now, such a framework should actually construct a process dependency graph with clearly defined interface variables, which can later help in detecting inconsistencies. And again, if such an inconsistency is detected, we can actually resolve it using automated resynthesis. So in summary, I have talked about different types of inconsistency. To start with, I have talked about the inconsistency in different phases of the synthesized process. And I have also said like such an inconsistency can be resolved through control architecture co-synthesis. And then I have also pointed out our future work that we would like to do something, we would like to come up with some framework which can actually manage interdisciplinary and interprocess inconsistencies. So this brings me to the end of this slide, and thank you for viewing this video.